Okay, so we're gonna scrap all the motivation for this one and not actually use a detailed real example for the sake of time. And we're just going to assume we know three facts. And I will, for those that find it helpful, I'll make a traditional rectangle for the entire space. Something from there, some elementary element is going to be drawn from in there. Right, this is the world of all the things that can happen. And we are going to call this circle A, and we'll call this slightly larger circle B, and note that what we're given is that the probability of A is equal to 0.2, it's 20%, 1/5, whereas the probability of B is 30%, it's equal to 0.3. Furthermore, we're given the probability of the union, so everything inside those two circles, anywhere in those circles, the A without B, the B without A, and the A intersect B, right? And so we have that union, the probability of A union B as being equal to 0.4, 40%. Okay. For the first question, finding the probability of A intersect B, right, the probability of both events happening, you might be able to figure this out intuitively. Let me just say, we'll do it a little more carefully in a second, but let's just think about this, what we know here. We know that there's the probability of A, event A occurring that inside that circle is 0.2, right? And we know the probability of B is 0.3. And we know their union probability of somewhere inside those, anywhere with the shading right now, is 0.4. So, what if those were totally mutually exclusive? They should add up, right? 0.2 plus 0.3. Because they're overlapping, you're getting some number smaller than that. You're getting 0.4. And so it may be evident, and we'll break it down if it's not, that this overlapping part is going to have to make up for the missing bit. That's going to wind up being 0.1, right? That would be counted twice if we were mistaken and added probability of A to probability of B to try to get the probability of their union. And if we took the point A is probability of A is 0.2, and we added to probability of B, we get 0.5, but in fact the union is only 0.4, so it would be the piece that we'd be counting twice would be that 0.10. Now don't worry if that made no sense whatsoever. I'm going to break it down, and you shouldn't rely on that sort of loose intuition anyway, so it's fine if you didn't have that intuition because it can lead you astray. I want to, let's just go back a touch and look at it like this. We have the probability of A intersect B is what do we know? Well, let me show you the first two thoughts that I have and think about whether we can use them. We know that probability of A intersect B in general, when they're not independent, we don't expect them to be, and we can let's just kind of write the general rule down, which is a chain rule or the general multiplication rule, that the probability of A intersect B is the probability of A times the probability of B given A. I think the first time I wrote it in the opposite order, which is fine because it's multiplication. Probability of B given A times probability of A. Or the probability of B times the probability of A given B, right? We saw that in the slides on this on these first handful of key probability facts. So we've got the marginal probabilities, probability of A. We've got the probability of B. Those are given, but we're not given any conditional probabilities up top. We weren't told those. So that in and of itself isn't helpful. Well, we didn't present it as a fact about the probability of intersections, but there is one rule that we have. If you're looking back, and you might want to pause this for a second. I did suggest that you try to go through these step by step and see whether you can come up with a strategy or for how to solve it. There is one place in those first key probability facts that the probability of A intersect B occurs, where it's not the star, but when you're given the general addition rule about the probability of, in fact, it's the third axiom, I believe, the probability of A union B in general, whether or not they're mutually exclusive, this will hold, although it's most helpful to lay it out when A and B are not mutually exclusive, and here they're certainly not. It is a sum of probability of A plus probability of B, subtracting off the probability of their intersection so you don't double count. And this is kind of what I was alluding to in what I said might be intuitive for you, maybe not. Why is that helpful? Well, the thing we're looking for is in this expression, and everything else, every other element is given in the problem, right? So we have probability of A union B is 0.4. We have probability of A is 0.2. We have probability of B is 0.3, right? Minus this thing that we want. If you want to, rekindle your algebra, we could say, if it makes it easier for you to think of this as, hey, this is X and we're solving for X, right? I prefer to keep calling it that thing that we're looking for, the probability of A intersect B. But we've got 0.4 equals 0.2 plus 0.3, that's 0.5 minus the thing we want. And if we were to, I could subtract 0.5 from both sides. I'll get negatives on each side. I'm going to go the other way. I'm going to add the probability of A intersect B to both sides to make it go away on the right. And I'm going to subtract 0.4 from both sides. I'm going to do it in one shot because I'm running out of room. Right? Probability of A intersect B is equal to, if I subtract the 0.4 from both sides, 0.5 minus 0.4, it's equal to 0.10. Right? That's this overlap. Right? A altogether is 0.2. B's probability is 0.3. We know the entire union of them is 0.4. So this has got to be the overlap, right? We got the 0.2 plus 0.3 would get us to 0.5. We don't want to double count that 0.10 in there.